So what we're asked to do in this problem is to find the critical points for the plane curve defined by the parametric equations. X of t is equal to t cubed over 3 minus t squared over 2 minus 2t minus 4, and y is equal to t cubed over 2 minus 2t plus 2. And we're going to be looking into the range, or into the values with t running from minus 5 up to 5. So just to get an idea of what this curve looks like, let's take a look at the graph. So to get an idea of what our curve looks like, we can have GeoGebra plot it. And what we have here is the image of the curve shown in red, and the blue vector is the position vector as our parameter t increases from minus 5 to 5. And so as we play that video, we get an idea of kind of the orientation that curve is going to have as we trace out the entire domain. And so what we're looking for here in this equation is, or what we're looking for in this particular problem, is to find the critical points for that curve. So at this point, it's probably a good thing to recall exactly what our definition of a critical point was. So a critical point was going to be a point on the curve y as maybe some function of x, where either dy dx was going to be 0 or dy dx is undefined. And so in this case, how do we get dy dx in terms of our parameter variable t? Well, for that, we can turn to the chain rule. So if we stop and remember that if we write dy dt, then as an intermediate variable, this is really going to be dy dx times dx dt. And so if we wanted just our function dy dx, we can write that in terms of the derivatives with respect to t as just dy dt divided by dx dt. And so when we're kind of looking for points where dy dx we're going to be 0, well, that's going to be the case when our numerator dy dt was going to be 0. And likewise, dy dx undefined is going to occur when our dx dt was going to be 0. And so when we're looking for our critical points, those are going to be found where the derivatives with respect to our parameter t are going to be 0. So let's see how that looks in this particular case. So when we're given our function x of t, then it's pretty straightforward for us just to compute dx dt being our t squared minus t minus 2. And likewise for our dy dt, that's just going to be given by 3/2 t squared minus 2. And so if we're looking for values where our dx dt was going to be 0, so we have t squared minus t minus 2 is equal to 0. Well, for that, we can turn to the quadratic formula, or we can just factor this equation, which is going to give us a t minus 2 times a t plus 1. And so we're going to have values where our derivative is going to be dy dx is going to be undefined when t is equal to 2 or t is equal to -1. And likewise, if we're going to find out where our derivative dy dx is equal to 0, for that we want to set dy dt equal to 0. So this is going to give us our 3t squared over 2 equal to 2. So our t squared is going to give us a 4/3. So we have values for t being plus or minus 2 over root 3. And so what we have now is actually four different values for which our parametric curve is going to have critical points. So we know that our derivatives are going to be undefined whenever t was equal to 2 and -1. If we kind of zoom in at particular points on the curve, we can see that, yes, this really does hold true. So what we see here is, as we're kind of zooming in on that loop of the curve, we see that when we're arriving at t is equal to -1, which is going to be up here at this point B, that we do have a vertical tangent line at that point. And then as we continue on around, t being -1, as we come back around, and then we hit t is equal to 2 at our point A, we see that again, we have a vertical tangent line at that particular point. And so likewise, we had our derivative equal to 0 at t is equal to plus or minus 2 over root 3. And for those values, we're seeing that those do correspond to horizontal tangents here at t is equal to -2 over root 3, and then here at our point C, whenever t is equal to positive 2 over root 3. So we're able to visualize those through GeoGebra as well, to see that where those tangents really do in fact show up on the curve just as the calculus predicts that they should be. So I hope you've enjoyed this, and I will see you guys next time.